Good morning. This is Mike McGinn, your online instructor for NetI 105, and today we are going to talk about Chapter 6, Network Layer in your NetAcad curriculum. In Chapter 6, we talk about what makes the internet kind of work. The network layer is the layer of data communications that can be routed from source to destination. It is what handles the movement of data from the transport and the upper layers to the data link and physical layers. So far in previous chapters we've talked about the physical and data link layer, and as you recall, that is all based on MAC address, which is unique to each individual network device wherever it is in the universe. So we've discovered how data physically moves. Now we're going to figure out how data logically moves and is routed from source to destination. So that is the gist of this particular chapter. In the network layer, there's two primary protocols that we deal with, and that's IP version 4 or IP version 6. So I'm sure you're familiar with IP addresses. I'm sure you've seen them so far in this course, as well as probably in your previous experience. But the IP addressing is what is used intelligently by intermediate devices such as routers and layer 3 switches to route traffic down various paths based on what's the most efficient and et cetera. There are some legacy network layer protocols, but they're not widely used anymore. One is the Network Internet Packet Exchange, or IPX, which is a Novell proprietary protocol. There's also AppleTalk and CLNS DECnet. I have not seen CLNS DECnet in decades. AppleTalk, it's been a while. IPX, it's been a while as well. It's been several years since I've been in an environment where that was still being used. So as I said earlier, what happens is that the data is packaged into a segment at the transport layer, and then is encapsulated into what is a packet in the network layer. So the packet is the PDU that we're going to be talking about, or the IP packet in the network layer. So the characteristics of an IP packet is they're much similar to a frame. Is you have an IP header, and then you have the segment, which contains the layer 4 data payload. So TCP segments are encapsulated into IP packets, and away we go. And then the IP packets flow through the internetwork. One thing that you need to be aware of related to layer 3 or IP packet communications is that it is connectionless. The receiver knows it's there, and it knows the receiver basically knows when does not know that it's coming. Let me restate that. It's connectionless, so the receiver doesn't know it's coming. It just shows up. And the sender doesn't know if the receiver's there, if what they've sent ever got there, and if the receiver can even read what I've sent them. So you're thinking, well, then how does this work? So IP or network layer protocols are unreliable. IP does not guarantee that all packets will be received. So other protocols manage that process by tracking packets and ensuring delivery, and primarily that's handled up in the transport layer with the TCP protocol, which we will talk about in chapter 7 or 9. I think it's 9. But anyway, we'll get to that later in the course, and you'll get a better understanding of how it keeps track of it. But basically, the way to, kind of a crude way of putting it is with IP, your computer just pukes it out and says, go where I tell you, and if the intermediary network is working properly, everything will get to the destination, but there's no tracking mechanism to make sure that it happens. The other thing is that IP is media independent. It doesn't care what it's traveling over. That packet will stay intact, and the only thing that can change in an IP packet as it moves from place to place is that some of the header information may change as it moves from device to device. So to generate IP packets, the transport layer is basically building segments, and then it then gets encapsulated into the IP header, which is the network layer PDU. So in 6131, it kind of shows you the dissection of an IP4 packet header. And this is a little bit confusing to read initially, but basically what it's doing is because we're limited on the screen and we can't take it out all 20 bytes, it's showing you the first 4 bytes and then the next 4 bytes and then the next 4 bytes and the next 4 bytes and the next 4 bytes. So these 5 rows represent these 20 bytes, and that is the structure of an IP header. Couple things to be aware of is that the first 4-bit binary value of the IP packet version, and that for IP4 is always 0100. Keep in mind all of this is binary, ones and zeros. Another important field to be aware of is the DS, or differentiated services field. And this is what does tagging for quality of service, so that say voice packets get priority through the network devices that it travels through, so that you don't have problems with jitter and things like that. You can also create tagging for specific applications that you want to get high priority service as well. The time to live is an important 8-bit binary value that limits the lifetime of a packet. Basically, what happens is every time that it hits a particular network device, that's considered a hop, and, where that packet is being routed. And if a particular packet has been routed more than the time to live, then the packet just drops. The reason why this is employed is if you've got a routing loop in your network. This allows so that, in theory, protects that network device from being overwhelmed by packets that are just coming back over and over and over again. The protocol, another 8-bit binary value, indicates the data payload type that the packet is carrying, so that it can pass it to the appropriate upper layer protocol. TCP is real common. Other layer 4 protocols are ICMP, which is what your ping command uses, and UDP, which is a connectionless layer 4 protocol. Then, of course, the source IP address and the destination IP address. Where am I coming from? Where am I headed? And then finally, there's some fields that contain some housekeeping information. The internet header length, which defines the total length of the header. so that, and then the total length of the packet, and then some checksum information as well. And this is all to make sure that when the packet gets received, that the receiver can determine that the packet is not corrupt. One other thing to keep in mind is a router may have to fragment a particular packet when forwarding it from one medium to another, and that is if the medium has a smaller what they call MTU um, to than the receiving media. And when this happens, fragmentation occurs, and the IP4 packet uses fields to kind of keep track of that split up information, and those are in the identification field, the flags, which tells it how it's fragmented and what the fragment offset is, etc. And then, of course, the header checksum has to do with validating that the packet is intact by the receiving end. So that's a calculated value, and we've talked about checksums in our discussion about frames. So based on all of that rather detailed information, what I would do is I would drill yourself on 6134 IP4 header fields and make sure that you can do this and master that. This all gets tested pretty heavily in the exams, etc. So, for example, if we're commonly referred to as hop count, that's time to live. Identifies the IP address of the recipient host. Well, that's going to be your destination address. Always set the 0100 for IP version 4. That's my version. Identifies the priority of each packet. That's going to be my differentiated service because that's referring to quality of service. Identifies the upper layer protocol to be used next. That's going to be my protocol. And identifies the IP address of the sending host. And it gives me a attaboy when I do it. And then I can reset it, and I can do it again. So I would run through that several times until you get them all right, and you feel like you understand what you're doing there. Okay, so then we start talking about IP version 6. And the reason why IP version 6 came out is because what they found with the explosion of the internet is that IP version 4 was going to run out of unique address space. And so the big problem with IP4 is that there's IP address depletion. There's only a limited number of unique public IP addresses available. Although, limited is 4 billion. The increasing number of new IP devices that are internet facing and always on connections, the potential of growth of less developed regions have increased, and the need for more addresses has just exploded. So you're starting to see in the last 6 or 7 years, you're starting to see IP version 6 on your network devices as an optional configuration mechanism for network devices. As time goes on, you'll see more and more actual implementations of IPv6. With that said, being a child of the 70s, we were supposed to be totally metric by 1980. So, I think IPv4 is going to be around a while. So what this allows is us to deal with some things that IP4 is limited with, and that is one, IP4 gets complex to be able to route, to make best path determinations. as the number of servers connected to the internet increases, so does the number of network routes. These IP4 routes consume a lot of memory and processor resources on internet routers. IPv6 is a more efficient way of routing. And then lack of end-to-end connectivity. The way that we are getting around the lack of IPv4 addresses is we're using a technology out there known as NAT. Basically what NAT is it stands for Network Address Translation, and most of your routers, your home router, your internet router that you have at home, is actually doing NAT. There's an outside interface that's got a public IP assigned to it, and then on the inside interface you have a local LAN address, usually like a 192.168.0.0 network on the inside of your home network. And then all your devices are being assigned a internal or a private IP on the inside interface. So that technology it limits some of the things that we can do with applications that are end-to-end, and it also makes it more complicated. So IPv6 is kind of the definition of overkill in terms of making sure we got enough IPv6 addresses. For example, as I mentioned earlier, there are 4 billion IP4 addresses, but there are 340 undeciline, I can't even pronounce that, undeciline IPv6 addresses. I didn't even know there was an undeciline. And that's just how unbelievably big it is. This kind of shows so you're basically 10 to the 36th power in terms of potentially unique public IP addresses with IP version 6. So in 6143, this is a good screen to study. It shows you the IP version 4 header field definition, as we've talked about, and then it kind of isolates what's changed in IPv6. The headers are very similar, but you can see that there are structurally some differences. So you need to familiarize yourself in terms of what is different between the two headers, etc. So the IPv6 traffic header, same kind of structure. You've got 40, each of one of these rows represents up to 40 bytes, and then so you've got 4 bytes here, 4 bytes here, 4 bytes here, etc. And it goes down to a total of 40 bytes for the total IPv6 packet. The IPv6 packet is larger than an IPv4 packet in terms of total number of bytes. So some of the fields, the version is a little bit different. It's 0110 instead of, what did I say it was for IP version 4, 0010. And the traffic class has replaced the DS field that's used for quality of service. There is a flow label field that is a special service for real-time applications. It can be used to inform routers and switches to maintain the same path for packet flow so the packets aren't reordered. So this is some higher level quality of service tagging that can be done. The payload length is the same as like the total length of field in an IP version 4 header. It defines the entire packet size, including header and optional extensions. And the next header is a 8-bit field equivalent to the IPv4 protocol field. It indicates the data payload type that the packet is carrying. I know it's kind of misleading in that it's called the next header. Enabling the network layer to pass the data to the appropriate upper layer protocol. This field is used if there are optional extension headers added to the IP6 packet. And of course you got a hop count just like you do with IP version 4 where we use the time to live. And then you have a source address and a destination IP. Excuse me, on 6146, there's an activity similar to what you did in 6126 with IP version 4. Allows you to line up your definitions with the particular fields. Again, I would drill yourself on that to get yourself very comfortable with it. Okay, so in section 6.2 we talk about routing, and this is kind of where the cool stuff starts to get discussed, and this will allow you to start to understand how networks make intelligent decisions on where to send packets as they arrive and get them off to their destination. In 6211, this is a very simple network, might be similar to something you have at home. And when you send a data to a PC that is on your local area network, basically what happens is it does an ARP lookup and determines that IP is on your local network and gets it there. It also will, if it's a destination IP that is not in your network, it sends it to your default gateway, which in this case is the inside interface of R1. Your default gateway address is whatever network this is, .1. And then that router makes a decision to send it on to your ISP, which through their cloud will get it ultimately to the remote host. So that remote host might be a Amazon.com web server or something of that nature. So that is in very simple terms what's going on routing on a local network. So a little more detail here. Our local network is 192.168.10.0. We have 192.168.10.10, 10.15, and 10.1. 192.168.10.1 is my default gateway. So if I'm sending something to any network that is not in the 192.168.10.0 network, basically the packet is sent to the router, and then the router makes intelligent decisions on where to send it from there, which in the case of a home network is going to be always out its only other interface, which is your outside or internet facing interface, and then routers in the cloud make decisions on where to send that packet so it ultimately gets to its remote network. So inside of a router, you have, and even on your PC, and here they show a netstat-r command from a command line, you can see what your routing table is so that it knows. So a 0.0.0 destination is basically your default route, which means that if it doesn't find a place to go in any of these others, it's going to go out that route, use that route to get where it needs to go. So this is how your PC determines, what the destination address is for a remote network. So it knows to route it to the 192.168.10.1 gateway out its interface of 192.168.10.10. So that PC is saying, okay, I got a packet that needs to go outside my network, and I want to say, okay, well, where's that network at? Oh, it's not here. Okay, I use my default route. Okay, that means I need to send this packet to 192.168.10.1, which is the inside interface of my default gateway or my router. And then it says, okay, now that I got it, I can send it on where I want to. So that's the magic. And the metrics are basically fields that determine what priority that route has in your table. So this section on 6214, give this a good read, kind of tells you what some of these routes actually represent. You've got a loopback route, and you've got multicast routes, which are the 224s, and uh, and then the broadcast and multicast are the 224s and the 255s, and things of that nature. Um, so give that a good read. Make sure you understand that. Okay, so when you're looking at routing on intermediary devices, things get a little bit more tricky. So in this scenario, we've got two routers, and each of those routers has three interfaces on it. So as a packet comes into that router, it has to decide which way does it go. And the way that works is that router has a routing table as well. Routers have two types of routes. They have directly connected routes. And these routes come from the active router interfaces. Routers add directly connected routes when an interface is configured with an IP address and is activated. So as soon as you bring up an interface on a router, there is a routing entry that's automatically entered into the routing table of that device. And then you also have remote routes, and remote routes can be manually configured or through routing protocols can be learned from other routers. And we'll get into dynamic routing protocols later. So this is a nice little graphic that kind of lays out the land of basically two LANs that are interconnected by a router. So you notice you have three different networks, several different networks. You got 192, 192, 168, 10.0, 11.0, and then you got 10.1.1.0, 10.1.2.0, and of course you've got the 209.165.200.224/30 network that is between the two, and we'll talk more about what the /30 means here in a while, but that's what's going on with routing. So when you look at a routing table in a router, on a Cisco router, the command is show IP route. You need to be in privilege mode to be able to pull that command off. And what it shows you right at the top is a kind of a little cross-reference or legend as to what all of the different codes mean. And basically what the codes tell us is okay, how did this router learn this route? And so, you've got local connected static routes, which static are manually configured, BGP, EIGRP, external OSPF, etc. These are all dynamic routing protocols, so you'll know what routing protocol made this particular router learn that route. And of course, then you get into the actual routing table here. So this is showing me I have the D is telling me that I have an EIGRP learned route here, and I got a couple of routes there. I've got a C route, which is a connected route, which is basically when it's directly connected, and so in this situation, I actually have interfaces networks that are subnetted, and we'll talk more about that later. But that is, and the route tells you what the interface is that it's going out, which in this case, this particular route, these routes are going out your gigabit 0/0, and these routes are going out your gigabit 0/1, and these routes are going out your serial 0/0. So in this scenario, these interfaces here between these two on this connection are probably a serial interface. The reason why I know that is because of this kind of communications emblem here. So this is basically your WAN connection. And then the gigabit Ethernets, typically those are black lines that would come off of those. So as I said, as traffic hits these routers, whichever direction they come through, that router is making a decision on what interface to send that packet out based on this routing table. So 6.2.2.3 really does a nice job of dissecting the routing table entries for you. Of course, column A identifies how the network was learned by the router, and in this example, it talks about that the route source of CNL represents gets created automatically whenever there's a directly connected network is created and the interface is configured with an IP address and activated. So this is your local route, which is basically the interface IP itself. And then this is the network that is attached to that interface. So 192.168.10.1 is the IP address of that interface and is the L. And then the 192.168.10.0 is this entire network up here, and that is has the C code. Of course, all of those are on gigabit 0/0, which is right there. So the destination network is always labeled B, and the outgoing interface is under the C column. So if you see an S out here, and that means it's a statically or a manually created route. That means that someone that got into to the CLI of the router and manually configured that particular route if you see an S. A D is that it was learned through EIGRP, which is an enhanced interior gateway routing protocol, which is a dynamic routing protocol. OSPF is another dynamic routing protocol. So those are really the only ones that you got to know for this particular chapter that you might be tested on. So when you look at learned routes in a routing table, things get a little bit more complicated, but I think if you understand how routing works, it becomes a little bit more logical or self-explanatory as to what they mean. As you know, we've already talked about that the D is the, excuse me, the D is the source code of that was how the network learned this particular routing entry. The destination network, which we've already discussed. And then there's where things get a little different. There is a field that is an administrative distance, which is the value that's before the slash in the next part of it. And that is a value that determines how trustworthy is the route source. You can configure a router to actually learn routes from multiple protocols, and you can weight how trustworthy you're willing to each one of those routing protocols are. So that's where that comes into play. The 217.0.1.1.2 identifies the metric to reach the remote host. So what this is all leading to is that if you've got static routes and multiple dynamic routing protocols configured on a router, you could have 3 different routing entries for the same destination network. So how does the router decide? Well, that's where the metric, administrative distance, and the metrics come into play. And then the next hop, which is your, you could look at it as what is the next router in line down the path to its ultimate destination based on what this destination address is. And this is a time counter that says when's the last time that we've learned from this particular routing source about this particular destination route, and then ultimately the outgoing interface of that particular route. So it's going to be out 000. So little bit more complicated, but you know, without dynamic routing protocols, the internet would just basically collapse. It would be an administrative nightmare to try to keep up with all the static routes and all the alternate destinations of or alternate paths to a given destination. And so dynamic routing protocols kind of allow the internet to be kind of its own ecosystem that you know can adapt and learn based on what is going on in real time on the network in terms of availability of interfaces, load of interfaces, etc. So you can be on the internet with Amazon.com, and you may have your first few mouse clicks, you know, actually create packets that get sent one path, and then your next few mouse clicks may send data that goes down another path, or you can even have a single mouse click create a data payload that will actually get broken up and go down multiple paths and then ultimately end up at the destination website. Pretty amazing stuff. So beat the heck out of 6.2.2.7 activity. Make sure you understand how that all works. They give you an example up here of a routing table entry. Make sure that you know which which definition goes in which particular column so that you can master that. You're going to be reading a lot of routing table entries in this course and also in future CCNA prep courses, so this is definitely worth your time to learn. Okay, and then in 6.3 we talk about the anatomy of routers, the physical device itself. You know, essentially the router is a computer. It has an operating system. It's got a CPU in it. It has to have a certain amount of RAM and a ROM as well. And also a router has special memory that includes flash non-volatile random access memory, or NVRAM, which is basically RAM that does, or RAM that contains data that doesn't get destroyed when the device gets turned off. Six point 3.1.3 router memory. This is something that you need to own in terms of knowing, knowing what's in what. For example, the RAM, which is volatile, you need to know that it's volatile, which means it gets destroyed if there's a power cycle of the device, which contains a copy of the iOS that is actually running, a running configuration file, and the IP routing and ARP tables, and the packet buffer. So when you hit the plug on that, pull the plug on a router, you're going to lose all that information. Non-volatile is the ROM chip that's on the router itself. It's got boot up instructions, basic diagnostic software, and a very limited iOS. NVRAM, which is non-volatile RAM, which means it doesn't get destroyed, has your startup configuration file. So when you kill RAM by power cycling device, when it boots back up, it copies your startup configuration file into RAM. That's why when you make changes in a router, or a switch for that matter, on a Cisco device, and you make those changes in CLI, until you actually copy that to your startup config, when you power cycle that device, you're going to lose your changes. So that's why when you make changes to a router, as soon as you're comfortable that those changes are all right, you want to write your configuration to your NVRAM. And then flash is, a lot of times these are like flash memory cards that contain the version of iOS that you're running, as well as other system files that you may need or have. You may get a question or two about the actual being able to identify what's inside of a router. This little graphic on 6314 inside a router does a good job of making you tell what is all the components of a router. So I would suggest you go through that. And then we look at the back plane of a router, and you need to be able to know by visual inspection what's what on the back of a router. Usually there's some slots for option cards. So for example, if you've got a serial connection on a router, there'll be a serial module that goes in there. If you've got a 10 gigabit Ethernet module, you would have one there. Um, so you've got some flash slots here. And of course you've got your auxiliary port, your console port, and remember your auxiliary port is if you wanted like a dial-up modem backup into the console of a particular router. And then you've got your two LAN interfaces, which are basically um, for by default built into the router. So without any of these modules, you can play with the router and set up some routes. And then a USB port, which doesn't get used much. So 6318 is good activity for you to do to really understand components of the router. Um, so I make sure you do that. And section 6.3.2 takes you through the router boot up process and what actually happens. You will be tested on this process and what goes in what order. You'll see questions where you need to put the steps in the appropriate logical order. So it's really important that you understand this graphic and that you know how that all goes through. It's pretty easy to understand. It's just there's a lot of information there. So just real quickly, how it boots up is it does your post and loads that from ROM, which is your boot up, and your bootstrap gets it from ROM, and then from Flash or a TFTP server, it grabs your Cisco iOS operating system and loads that operating system. And then from there, it gets your configuration either from NVRAM TFT server, or you manually entering it into the console. By default, if you can't locate a configuration file, it goes into setup mode, which is what you have to do from the console. So this takes you through that whole process. So, so really, what it amounts to is these are the source of the information in the order that it reads them, and then this is what it gets, and then this is what it's doing. And they talk about the show version command, and what that information that tells you. It tells you some nice information, such as what iOS version you're running, what your bootstrap is, where it got its iOS, the amount of CPU and the amount of RAM, which is really important, especially if you're looking at doing any kind of feature upgrade to a router. You got to make sure that whatever you're going to install on it's going to run based on the resources that router has. The interfaces that are attached to it, and the amount of NVRAM and flash. So so there it tells you the interfaces, tells you your non-volatile configuration memory, and what your compact flash memory is as well, which is your flash, and this is your NVRAM, your interfaces, and how much memory you've got and how much is available as far as RAM in the on the device, where it got its iOS and what the file is, and then what version you're running. So it's all there. You just have to basically dissect it, and this section here kind of helps you figure that out. There is a video at 632.5 that I would suggest you view that tells you about more about the booting process, as well as there is an activity at 6.3.2 that is also another reinforcer of that whole section. So in 6.4 we talk about configuring a router. There's going to be some labs and packet tracers on that, so I'm going to not go too much into that. Other than what you have to do is obviously to do anything significance in a router, you've got to be able to log into it through a console port. You have to enable yourself to get into privileged exec mode and then get into a global configuration mode, and then all good things happen from there. And so it'll take you through doing some of that in the labs, etc. Also talks about how to configure interfaces like assigning IPs, and how to verify those, as well as configuring the default gateways. And again, there's packet tracers that's going to reinforce all of this. This is important stuff. This is stuff you're going to have to do in your sleep by the end of this course. So definitely spend a good time on your labs and packet tracers in this particular section. So there is, at the end of this chapter, a packet tracer skills integration challenge. That is a good exercise to do that basically allows you to get a network set up, you know, um, from front to back, and configure it appropriately. Doesn't take you, if I recall correctly, doesn't take you step by step on how to do it. It pretty much gives you all the information and says, okay, take what you've learned and do it. So there's not a lot here in terms of instruction. You just got to take what you've learned and apply it. So definitely wouldn't do this until you've done some of the other packet tracers and got yourself familiar with router basics. But this will challenge you a little bit. Okay, so that's chapter 6. Enjoy. You're starting to get into the meat of configuring um, Cisco network devices, as a Cisco router is a layer 3 device or a network layer device. That it's appropriate that we learn to configure those at this point and in this chapter. So good luck, and I'll talk to you again soon.